Hey, what we're looking at today is building off of what we had just got done looking at the other day, and that is taking now the opposite we did. Instead of writing formulas, we're going to be writing names of ionic compounds. And basically it's not a lot different than what we just did with writing formulas, except that what we're going to be doing is pretty simply, there's only one little catch that we have to kind of worry about at times. So for example, let me just take a couple of simple ones for us. One that we already all know, NaCl. How do we name this thing? How do we come up with a name for this ionic compound? Very simply, what we're going to do is basically two steps. Step one, we're going to write the names of our ions. Remember, these things are always going to be binary, so there's ever only going to be two ions. And that's going to be important as we get to polyatomic ions and some of those things like that. But step one, write the names of your ions. And step two, we need to check the metal to see if it has more than one charge to it. Because if it does have more than one possible charge to it, then we're going to need a Roman numeral. Okay, so we're going to use that. We're going to look at our periodic tables, but that's our basic steps that we need to do. So how do we take a look here at this case? And what do we do with NaCl? So let's start, again, it's a very simple, and we already know what this is. We know a compound is ionic if it starts with a metal or NH4. Okay, Na is our cation. It's a metal. That means that that's our cation. Everything that comes after Na is the anion. So Na, we name metal cations by calling it sodium. Now in this case, we don't have to put the word ion after it because it's in a compound already. And then Cl is chlorine, but cation or anions, we drop the ending and add ide. So there you have sodium chloride. Let's take another example. Let's say we started with NH4 in parentheses 2O. Hey, what do we start with? Oh, hey, look at that. It starts with NH4. That we know is our only polyatomic cation. So everything comes after that, that's our dividing line, is our cation and our anion. NH4 is ammonium. O is oxide. Okay, kind of hopefully getting the handle of that. Let's take a look at something that's a little bit more advanced than that. So let's take a look at, let's say I have Ca parentheses C2H3O2 2. Uh-oh. Does this calcium, carbon, hydrogen, oxygen? No, it's not. Because according to our rules, Ca is a metal. That is our single cation. Everything that comes after that is one anion. Ca is calcium. And then that whole other thing, since there's more than one atom present, it has to be a polyatomic ion. So we look at our polyatomic ion chart, and that is acetate. Now what I haven't done yet on any of these is look at my periodic table to see does my metal atom have more than one possible charge or not. And so far they haven't. Calcium is only a +2. So that's the end of it, calcium acetate. If we have NH4 to SO4, the same rules still apply. What do we start with? We're starting with NH4, which is our cation. That means everything after it has to be the single anion. So, and we find that then on the polyatomic ion chart. Ammonium sulfate. Okay? Now let's go to something that has a charge on it. Because once we have a charge of more than one possible charge, what do we do next? So let's see, let's pick something like MnCl4. Okay, so when I look at MnCl4, Mn is my cation, and that is manganese. And Cl is a monatomic anion, so that's chloride. But when I look into my periodic table, right above Mn, I see a whole bunch of different possibilities. That means I need a Roman numeral here. Without that Roman numeral, I will not be correct. How do I find out that Roman numeral? Well, what we're going to do is we're going to do a little bit of math. And Roman numeral is just the charge again too. So what we're going to do is we're going to look at our anion. We always know what the charge on the anion is. In this case, chlorine, or the chloride ion, we know is a -1. So what we're going to do is we're going to take the charge of our anion and we're going to multiply it by the subscript, or how many of those there are. So -1, and there are 4 chlorides, so that gives me a -4. That's my total negative charge. So I have a little total of -4 up here. Well, in ionic compounds, or all compounds, our net charge has to be 0. So that means we have to have a total positive charge of +4. As I look at this then, that's the total positive charge. How many manganeses do I have? I have just 1. So what I have to do then is I'm just going to take every single manganese is going to be a +4. So I'm going to take the total positive charge. The last thing I'll do here, I'm kind of getting all over the place on the screen. I'm going to take my total positive charge divided by the subscript on my cation, and that is my Roman numeral, manganese 4 chloride. One more quick example in this case. Let's do, how about SnCO3. Okay, Sn is 10. That's my cation. CO3, oh, that's got to be a polyatomic ion because there's more than one atom, and that has to only be one other ion in this place, and it is carbonate. Okay, and I look at my periodic table in my second step to look at tin. Tin has more than one possible charge, so I'm going to need a Roman numeral. So what do? I look at the carbonate. Carbonate is a -2. How many carbonates is there? You might be wanting to say 3, but there's actually only 1. If I want to have more than one carbonate, I have to have parentheses around it. So -2 times 1 is a -2. That means my tin has to be a +2. 2 divided by 1 is 2. Tin, 2 carbonate. And let's see, one more example. And what you might think, oh, hey, what if I just is able to take this and uncrisscross? I'm going to use PbO2 as an example. Pb is lead, O is oxide. Lead has more than one charge. If I crisscross this, I would say it's lead 2. If I went back, right? Now here's the problem. If I do it mathematically, oxygen is a -2. So -2 times 2 is a total of -4. That means I have to have a total of +4 for the one lead, which means that, guess what? It's not a lead 2, it's actually a lead 4 oxide. So you don't want to just uncrisscross, because that's not always going to give you the correct answer. You have to make sure, because things are reduced, you have to look at that math and do the anion times its charge. You get the total negative charge, which is equal to the total positive charge, divided by your subscript of your cation, and that's your total positive charge. Okay, so that's our look at polyatomic, writing ionic formulas and names.